All right, we're going to get started. So it's my great pleasure to introduce Brandee Carlson, who's visiting us from the University of Houston, just down the street. And she is, I found out last night, an alumni of University of Texas. And I think everyone else knows this except for me, maybe. I invited her because I really wanted to hear about her work on deltas, especially because she's working in the Arctic on deltas, and we are working on our own version of deltas. And we had a fun talk this morning thinking about how deltas work in the glacial environment. But Brandee comes from the hydro program here at UT. We have Jack Sharp here to represent that program. And she graduated with an undergrad research project with Wonsak Kim, if you remember Wonsak. And then she went on to Rice University, where she worked with Jeff Nichrower to get her PhD, and then did two postdocs, the Vanderbilt one, and then one, it was a NSF EAR postdoc fellowship though, which is pretty hard to get. And then she did another one at Colorado with Irina Overeem, and then she got her job at the University of Houston, where she's been for the last 3 years. So she's just down the road. If you have any follow-up questions, you can always like send her emails and stuff. But yeah, please join me in welcoming Brandee to give a talk.
All right, thanks so much, Ginny. Okay, so today my topic is shifting sands, so how humans and climate keep our river deltas on the move. Let's see if I can switch this. Ooh. Okay. Oh, okay. Okay, so as Jenny mentioned, I am an alumni of UT. And so for this talk, I dug up a picture of me actually at the Pickle Research Center. So this was about 12 years ago. I was conducting delta building experiments with Wonsak Kim on this campus before heading over to Rice to continue my kind of interest in the pursuit of delta dynamics. So currently my lab at UH studies delta building processes locally. So I work in several bays in Texas. I'm also working actively on sedimentation in arid reservoirs and in Arctic fjords, which those Arctic fjords are going to be the topic of conversation today. Okay, so direction here. Okay. So why do we care about deltas? Of course, we know that many deltas are at risk due to reduction in sediment supply, accelerated subsidence, the leveeing of rivers, and sea level rise. And this obviously has huge implications for systems like the Mississippi, which are experiencing pretty rapid retreat of shorelines. Nope. Okay. So deltas build through a process called avulsion. So this is just simply the relocation of a river channel. So for the Mississippi, this happens on about 1,000-year timescales, where wherever the active channel is located, it's actively depositing sediment and building a lobe. And then it will switch to another position after some time. And this avulsion process is basically what controls the distribution of water and sediment across a deltaic shoreline. And so it's the amalgamation of these lobes that forms a delta. But humans like to live on deltas. And humans both directly and indirectly impact the sediment dispersal pathways of deltas. So here I'm showing an example of the Yellow River Delta. So this is in Northeast China. This is an incredibly sediment-laden river system. And it, of course, avulses just like the Mississippi, except that the natural avulsion timescale of this system is about 10 years, okay? So 10 years compared to that Mississippi, roughly 1,000. So what I'm showing in this map here is, this blue line is showing the current active location of the Yellow River, and surrounding it, each of these black lines is showing an abandoned channel pathway. So in this system, some of these channels have been abandoned naturally through that avulsion system, but also, this is a huge flood risk when we have a channel change its path on a highly populated river delta. So Chinese engineers also purposefully reroute the river, and they happen to do that roughly around the same time scale as the avulsion time scale. So roughly every 10 years, they're anticipating it. So what that means is, with a system like this, we end up with this kind of range of both naturally and engineered kind of abandoned delta lobes. And it turns out the way that we engineer those abandonments has significant impacts on the retention of land around shorelines. So here in blue and in yellow, I'm showing basically shoreline position over time for some recently abandoned delta lobes. These two were abandoned through engineering practices. And then we have a more recent one in orange that was abandoned through a natural avulsion. And kind of the take-home message here is when we engineer these diversions, the shorelines retreat at a rate that is about 4 times higher than when we have a natural avulsion. So this is kind of an example of humans really impacting that sediment dispersal pathway. Okay. So humans also, again, directly and indirectly impact those sediment transport pathways. So if everyone in this room agrees with me that we have a connection between greenhouse gas emissions and rising atmospheric temperatures, okay, resulting in atmospheric warming, this actually manifests in high latitude systems as an increase in sediment delivery to our fluvial systems. So this is a model from Jaya Savitsky, where on the x-axis we have surface temperature, and on the y-axis we have sediment load. And for every 2-degree increase, we predict an increase in sediment load of about 30%. And that's specifically for the Colville River. And we have examples of how this manifests. So this is an example from Southwest Greenland. This is a study by Meta Ben-Dixon, where she tracked shoreline progradation rates of deltas that are building into fjords. And each of these blue squares is showing a delta that's prograding, and each of the red ones is showing a delta that is eroding, okay? So we have this dominant signal of delta progradation in Southwest Greenland, where the size of those squares corresponds to how much growth we're observing. Okay, so this is probably not news to most of you in here, okay? So over the past 4 decades, the Arctic has warmed at a rate of about 4 times faster than the global average. And because Arctic deltas host ice in the form of land ice, sea ice, and permafrost, we have the ability to interrogate how ice loss manifests in these deltaic systems. Okay, so first, this is a study from Herein 2010, where in places where we have observations of water discharge, she compiled discharge data between 1977 and 2007 and looked at the relative change in meltwater discharge over that time period, and found that almost every system that she looked at in the Arctic had an increase in water discharge. And she also found that with rising atmospheric temperatures, we're basically changing the peakiness of that discharge curve, where we had lower overall peaks in water discharge, but we had more water over a longer period of time. Okay. So Permafrost, again, is one of these forms of ice that are controlling delta dynamics in the Arctic. So here I'm showing a modeling study from Lausanne et al. 2019, where permafrost was input in this model as a form of bank cohesion, and a delta was allowed to evolve. And what this study found is that when you have a high percentage of permafrost, we tend to see channels that stabilize and focus flow. And as we lose permafrost or do not include permafrost in the substrate as cohesion, we have a much more mobile channel network. Okay. So those are the kind of components that are going into this increased sediment load of sediment to our Arctic systems. Okay, but kind of to counter that, another process that's happening on many of our Arctic shorelines, especially continental Arctic deltas, is bluff erosion. So basically, when we have sea ice along our Arctic coastlines, it can protect the shoreline from wave energy, but the more time period or the longer the duration of open water, the more wave energy can erode our Arctic coastlines. And so we also kind of know that competing with this increased input of sediment, we also have fairly high rates of coastal erosion in some systems. So this one specifically on the Beaufort Sea is about 14 meters per year. And these high latitude systems have additional complexity, right? Because land ice in the form of, say, like an ice sheet has major impacts on what relative sea level rise looks like. So this top figure, on the y-axis, I have time before present, and on the y-axis, I have relative sea level rise and fall. This top plot is showing some coastal regions in Greenland and Baffin Island, which overwhelmingly are experiencing sea level fall over the last 10,000 years. Whereas many of our continental deltas are experiencing sea level rise. And just as a heads up, a system that I'm going to focus on today actually has very little sea level fall. So I like it because I can kind of ignore that component of it in later analyses. Okay, so we have these kind of competing factors going on here that deltas might respond to. So this increased sediment load, increased coastal erosion, increased channel mobility, increased river discharge, and glacial isostatic rebound. So how will deltas respond to that? Well, we're going to take a look at a couple of actively building delta systems, both in Baffin Island and Southwest Greenland. And we're going to take kind of a source to sink walk through these systems, okay? Where our source is going to be the ice sheet and the glaciers that source melt water and sediment at the ice margin. From there, meltwater picks up sediment, and we transport that sediment through progrlacial rivers. And we build deltas along the way. And then we will reach basically the shorelines of these deltas and look at subaqueous sediment transport out of those deltas. So we're going to start basically the talk with this QS in. So inputs of meltwater discharge and sediment in these systems. Okay. Okay, so this is drone footage from the ice margin in Southwest Greenland. So, you see, this is a Lever Glacier, and then we have a progradation stream exiting, and of course you can see these large terminal moraines, and these moraines are comprised of like all sediment sizes. So we have everything from like boulders to clays at our beginning. And progradation rivers sort this sediment, okay? So, we start with, again, a really wide distribution, but overall, really coarse sediment upstream, and we fine it downstream. So I kind of compare these systems to like, a set of sieves where hydrodynamically, by the time we get down to the delta region, we pretty much exclusively have something between coarse and then coarse sand, and then in the subaqueous area, clays. Okay, so in this system, which is about here as an example, is about 40 kilometers long, we see a 99% size reduction from that short source to sink system. Okay, so we want to know, kind of what are the characteristics of this transport system? And some Arctic fjords, we have discharge is monitored. So this is an example in Quinnguata, Greenland, where there is a bridge, and attached to this bridge, we have downward looking LiDAR. And this is nice because we can actually make observations of water discharge over time. So here I'm showing for one, an average between 2006 and 2020, where typically we have the onset of melt, and we pick up in our discharge starting around June, and then we peak late August, early September, and then we have a decrease again in our meltwater pulse in the fall. But for most of these systems, we do not actually have observational data. And because I am interested in the delta dynamics that are forming these systems, I want a way to at least make a first order estimate of what discharge might be. So my lab and I built, or we didn't build, but we employed a modified positive degree day model. Okay, so a positive degree day model, its most simplest, basically says, the atmospheric temperature is something over 0, and that warms ice, and that generates ablation. Okay, it is so simple that it's kind of easy to break it. So we employed this modification put out by Sai and Ruan, where we introduce a percolation layer. So basically what we say is, we are going to take some atmospheric temperature, and we are going to assume some temperature at a glacier surface, and we are going to warm some thickness of ice that is below 0 up to 0, but we will not have ablation until we warm that entire thickness. Okay, and those are the equations that basically allow us to first warm our percolation layer and then ablate that ice after the layers above 0. Okay, so I'm going to show examples from kind of 4 different regions. Again, we have Quinnguata, and then we have 3 systems that are on Baffin Island. So what do we have starting this model? We have temperature that is measured or modeled, at least, and reported for somewhere nearby. We have DEMs of our glaciated regions, and we have delineated catchments. Okay, so what we're going to do is we're going to take our atmospheric temperatures and apply an adiabatic lapse rate and predict what temperature is across our glacial catchments. Okay, so we can do that. There's Quinnguata for an example where we are kind of, applying this model temperature across the catchment. Okay, so now that we have that temperature, what we want to do is, of course, warm our percolation layer up to 0. And we do that by employing this equation here. And basically, this percolation thickness, right, is also not something that we're necessarily observing, right? So this model, employing this model, it's really quite sensitive to that percolation depth thickness. And so, if you play around with what that thickness might be, you're essentially controlling the timing of your predicted ablation. So we'll get into this, but we tested this for a range of percolation depths. Okay. So now we're going to say that we warmed all of our ice to 0, and we're going to start ablation. And, ideally, we're taking that ablation and we're saying, this is the melt water that we are generating. That is the discharge that is moving through our progrlacial rivers. But we want to know that this model is operating at least somewhat well. And we're going to go back to Quinnguata where we actually do have that observational data. And so what we did was we played with parameters, including percolation depth and our adiabatic lapse rate. And we looked at our modeled prediction, where our modeled predictions are in gray for that range. Here, the range of different lapse rates, down here for a range of different percolation depths. And we compared it to our observed data. And we used some correlation coefficients to try to optimize a choice for percolation depth and lapse rate based on the model versus observed data. So what we see is the modified model does a decent job of getting the peakiness right. The timing is pretty good. And it's order of magnitude matching. So, we're going to roll with that. We're going to roll with it, and then we're going to apply it to totally unmonitored systems. And when we do that, so for these 3 systems, here again, I'm plotting that range in values that we kind of allowed to vary for percolation depth and for the lapse rate. And, we think to the order of magnitude, we hope that that's performing decently well to get discharge, okay? And we want that discharge so that we understand what's going on in the downstream deltaic system. And other people have thought about these exact systems, okay? And they've certainly come to the same agreement. So this is a paper by Alexander Normando, 2019, where they collected bathymetric data along Baffin Island, specifically along delta fronts in fjords. And so they come to this conclusion that the percent of glacial ice in a watershed, so basically the amount of meltwater that is being generated, corresponds to the delta front morphology of these delta systems, okay? Where they're basically saying when there's more ice and there's more melting, they think that there are more turbidity currents that are being generated along these delta fronts. So more density-driven flows along the delta front. And I think that's great, but I also think that there are deltas that are, in between that ice catchment and the subaqueous environment that they measured. And so that study really piqued my interest and made me say, what's actually going on in the distributary channel networks in between. So we're going to move into what I'm calling delta S. So my temporary sediment storage along the progrlacial river and delta system. And we're going to investigate deltaic channel dynamics and delta progradation. Okay. And, like I said, many of these deltas are actively growing. So we're returning back to this figure just as a reminder. These are systems that have very, very high sediment export, and based on very limited data and remote sensing, studies have suggested that the Greenland coastline is responsible for 8% of our sediment delivery to the oceans globally. So we're really talking about a lot of sediment that's making it through here. And we expect, based on our existing understanding of delta building dynamics, that as we have shifting discharge and sediment load, that this will in turn kind of impact some of our channel dynamics. So we expect or could predict that if we have increased sediment discharge associated with atmospheric warming, we may also see enhanced river migration along our deltas. Okay, so we're going to investigate that. So we did this through a remote sensing technique where we basically delineated land versus water pixels on these deltaic systems. And we did this with basically every cloud-free image available in the Arctic. And we summed them together and looked at them over time. And what we find is certainly so these are the channels that comprise this delta. We basically see that they have high lateral mobility on annual and decadal timescales. And we can then, partition these data to ask some questions like, are there any kind of preferential flow paths in these systems? So, so here at Quinnguata, I partitioned between kind of what I call low discharge, so less than 1,000 cubic meters per second, high discharge, so over 1,000 cubic meters per second, and looked at how that impacted how frequently any specific pixel is wet. And so what I find is that, if I look at low discharge images, I have this pretty well-defined flow path in Quinnguata. So if I then compare that to what's over 1,000 cubic meters per second, I can see that we have this kind of more diffuse flow path that emerges as kind of what you would expect, except that I think what's really notable is kind of no matter the discharge condition, the channel seems to have an extremely preferential location for its channel mouth. Okay, so we applied these to the baffin systems. That's actually Kinger again. These two are the baffin systems, and we kind of see two distinct channel patterns here. One where we have sort of easy to delineate channel pathways. So I call these persistent channels. And then we have these more kind of diffuse flow paths. And so these two systems are maintaining 1 to 2 channels at their shoreline over the observation period. While if you look at a system like this, it's honestly like not even clear how many channels are actively anywhere at one time, kind of always over 5, but they also kind of migrate consistently. And a shoreline like this ends up within a year being channelized at one point or another, like 100% of the time, whereas these two systems, are maintaining channelization along the shoreline about 30% of the shoreline. Okay, so, we did this model to look at what the river discharge might be coming in. These two values are modeled river discharge. This is an average peak discharge for Quinnguata. And of course, these systems are not just influenced by rivers. There's also really significant tides in the Arctic. So we estimated what the discharge due to tides might be. We kind of followed a procedure laid out by Jaap Nienhuis and did a comparison of the influence of river versus tidal discharge. And we end up, finding that, for these two systems, the fluvial discharge significantly outweighs the tidal discharge, whereas in a system like this, the tidal discharge totally dominates the discharge signal. Okay. And, again, why do we care? Well, these relationships, these magnitudes of discharge of fluvial versus tidal discharge have big implications on sediment dispersal across a shoreline. Okay. And what I want to kind of put forth is that, this exercise, right, we are looking at channel pathways on the subaerial delta, but the delta, of course, it does not end there. There's a significant subaqueous component, especially in these kind of deep, several 100-meter deep fjords. So, now I want, I guess what I'm conceptualizing at this time is that wherever these mouths are located, that's where we're, of course, focusing the flow of water, but also sediment deposition and loading. And we know that rates of sediment loading compared to compaction can cause instabilities in sediment deposits. So this is a study by Dugan and Flemings, where they basically modeled effective shear stress and overpressure on some sediments in the New Jersey continental shelf. And basically what they find is that where there's an old delta toe that is prograding across these Miocene sediments, we have basically the least stable deposit here. So we've kind of primed this with a low effective stress that may lead to some instability in the deposit. Okay, so taking that in mind, knowing that these channel mouths are redistributing sediment across the delta front, we're now going to see what the delta fronts actually look like for these systems. Okay, so here's Kanger. So this is bathymetric data that was collected by my group in 2024. And these are two surveys from Norman Doe. And these labels, persistent and diffuse, these are the labels from the wetted frequency analysis. So that's actually from the distributary, the subaerial distributary system. I'm not using them to describe the bathymetric data, though. You probably notice that it looks like there might be like some linkage there, where our kind of deltas that have a persistent channel mouth location tend to have these like really nice, well-developed subaqueous channels, whereas our more diffuse system has this delta front that's just kind of like riddled with gullies and bed forms. For the rest of the talk, we're really going to zoom in on Kinger and analyze some of this bathymetric data so that we can try to understand flow conditions on the delta front. Okay, so this is taking us to our sediment discharge out, our QS out for subaqueous sediment discharge export. Okay, so again, we're in Southwest Greenland, right? We are in this system where the ice margin has significantly retreated. So these are all like progrlacial fluvial systems. And I like this system because it's monitored. We know that this system, since it's been monitored since the 50s, we know that we have an increase in water discharge over time related to those increasing atmospheric temperatures. Okay. And we know that this is a delta that is prograding. And so it's actually prograding at a rate of over 4,000 meters squared per year. And that attracted my postdoc advisor to work here in the early 2010s. And in 2010, she actually deployed a time-lapse camera that was pointed at the shoreline of this delta in Quinnguata. And what she ended up seeing, like initially she was interested actually in plume dynamics, but what she ended up seeing was that during the melt season in September, there's actually this like really large piece of the shoreline that kind of disappears and never re-emerges. And she, speculated that it actually, failed. So we possibly had significant transport from this delta lip to deep water. And so we asked this question, we have this very actively prograding shoreline, but is that mediated by possibly delta front failures? And this is a significant amount of sediment that we're talking about here. So if we orthorectify this, we find that it's between somewhere 200 to 500 cubic meters, which is between 11 and 20% of the total sediment load annually for this system. Okay, so what we did was we wanted to learn more about this system. And so we got a fishing boat and we attached a bunch of equipment to it, including an echo sounder, multi-beam echo sounder, an acoustic Doppler current profiler to get flow velocity. We also collected grab samples to get sediment grain size. We collected water samples and more. Okay, so again, that's our bathymetric survey that basically picks up just past the delta shoreline. And, we were able to get very, very shallow in our boat. And we ran our survey out to along the channel to about 175 meters deep. Okay. We're going to use the data from the bathymetric survey to do two different kinds of analyses for flow reconstruction. One that will focus on bed forms. The other will use channel geometry to predict the discharge of that might be carried in this turbidity current channel. So so we're starting at the proximal turbidity current channel A to A prime. We see we have these bed forms kind of all along this transect. We can interrogate and apply metrics to these bed forms. So we use some techniques from Zomer et al. 2021 to decompose our data and basically identify where bed forms are, how high they are, what the wavelength is, and the angles of the star and the leaf. And so can generate data like this, where we can look at both kind of these primary bed forms. So what's setting kind of the long wavelength variation of the channel bed, as well as our secondary bed forms, so smaller dune forms. And in general with this survey, what we see is that our dune heights are fairly small. They're pretty much always less than 1.5 meters. The wavelengths are fairly short, usually around 20 to 50 meters, always less than 200 meters. And we have super, super low star and lee angles across this entire survey. How am I doing for time? Okay, 15 minutes. Okay. Okay. So we like take a close look along this this first meander bend. We can see again it's riddled with these bed forms, and there's this nick point, maybe plunge pool that's downstream of it. So we can see how the bed forms change upstream and downstream of that nick point. We actually see that they're pretty similar in terms of their metrics of similar height, similar wavelength. We have a bit of a decrease on our lee slopes on the downstream side. And just overall, if we compare our proximal to our distal bed forms, we see like the strongest pattern that we've seen so far is that both the staw and the lee slopes like shallow downstream, but they were honestly pretty shallow to begin with. Okay, so now we're going to take that data, we're going to take that information, and we are going to try to reconstruct flow conditions from those bed form characteristics. So based on the data that we saw, I'm calling what's on the channel bed dunes. We can discuss that decision later. The way that this diagram defines cyclic steps has a much longer wavelength than anything that I actually observed in the data. So we're going to roll with dunes for the time being. But to evaluate the stability diagram, we need to know grain size, which we have. So we were throwing this petite ponar off the side of the boat. We collected sand, we collected shrimp. So it's my grad student that was responsible for collecting and processing that multi-beam data, influenced by the shrimp. Essentially what we end up seeing is that for the samples that we were able to get within the turbidity current channel, this is from 2023, it's largely comprised of fine sand, okay? So now that we know our grain size, make an assumption about what kind of bed forms we have, we can extract the predicted mobility parameter. And this is a parameter that's going to allow us to basically back out flow velocity from the system. So, I'm estimating a mobility parameter range between 0.5 and 1. And I basically used some basic parameters to solve for flow velocity and ended up coming up with this range of flow velocity ranging, 1.3 to 1.9 meters per second would be the formative velocity for those dune forms. Okay. We can also reconstruct flow velocity using channel geometry. So these are some cross sections of the channel, and this type of flow reconstruction basically takes into account the change in elevation between levees over some distance. So you're basically setting up a super elevation across the channel, and we are using channel geometry, so the radius of curvature, to predict what flow velocity might be around this bend. And we do that. In this instance, we predict a range of we predict about a flow velocity of 3 meters per second, so much, much faster than what we predicted with those bed forms. Okay, but that's not all, because we had an ADCP in the field also. Okay, so we're going to kind of test these models against some of our observational data. So we're going to look at an ADCP transect from A to A prime. Okay, so we sat for long periods of time with our ADCP running kind of over this turbidity current channel. And occasionally, we saw that we had kind of these high velocity. So here, the color, okay, let me back up. Here, we have depth on the x-axis. This is a cross channel on the y-axis. And these colors, so the warmer the color, the more yellow the color, the higher the velocity. So occasionally, we would observe these higher velocities near the bed of what we think is the turbidity current channel, okay? And when we saw these higher currents, at least from what we can measure, we're resolving about 10 meters of that high velocity flow, and we're seeing velocities of up to 1.5 meters per second. But these are pretty intermittent. So we were seeing something like this about 8% of the time that we were in the field and monitoring. So if you take kind of all of these ways to estimate what discharge might be through this turbidity current channel system, so using channel geometry, ADCP, and bed forms, we end up with this pretty wide range of predicted turbidity current channel discharge, ranging from 5,000 cubic meters per second, an estimate from bed forms, to 36,000 cubic meters per second from channel geometry. But of course, I'm after the sediment. So what I actually want to do is take these predictions for water discharge and eventually get at a sediment discharge by knowing something about the concentration of these flows. Okay. But just to make the point, okay, so here in blue, I'm plotting the fluvial discharge for 2023. So this was during our monitoring period. And each of these bars is showing the water discharge that I predicted from bed forms, ADCP, channel geometry, bed form max. Okay, the water discharge for one of these near bottom current events, it exceeds sometimes by orders of magnitude the fluvial discharge. Okay, so we measured suspended sediment concentration in the field, albeit not in a turbidity current, at least not yet. So what we can do is use the data that we have. These are gross underestimates of what concentration could be. But if we take what we have, we can estimate a range of 1.9 cubic meters per second to over 20 cubic meters per second of sediment delivery through that turbidity current channel. Okay, and just to bring that home, okay, sediment discharge in the fluvial system, it's about 0.4 cubic meters per second on average. Okay, and with our observations and our flow reconstructions, we're measuring much higher rates of sediment discharge. But do not forget that this is in a prograding delta. So even though we have lots of sediment that's likely being routed through this turbidity current channel, we are still able to prograde this shoreline. Okay, and even if you don't care about delta building dynamics, you probably do care about buildings and transport infrastructure and concrete and asphalt and probably electronics, including your cell phone. And, sand is a key ingredient for all of that. And, what this talk has focused on today are really these huge accumulations of sand. And, as we're moving into a continuously building and industrializing world, knowing sand budget in these systems could become important if it's ever economical to transfer this sand elsewhere, and will most certainly impact the delta dynamics if humans start interfering with it. Okay, so in summary, fluvial and tidal discharge may influence distributary channel networks and in turn, delta front transport networks. We looked at a delta front in Greenland that exhibits a well-developed turbidity current channel that actively transports sand. And we find that, when this turbidity current channel is actively transporting sediment, it exceeds that of the fluvial system between 4 and 35 times. So I'll leave it there. Thanks.
All right, is there any questions from the audience?
Microphone. Oh, okay. This one's more fun.
Thanks, Brandee. This is really cool. I care about sand. I also care about ice sheet history. And you've built this really neat linkage between ablation of the ice sheet, discharge through these systems into the subaqueous delta, and then related the channel geometry, the subaqueous delta to the ice sheet discharge. So could you look at all of these old, non-active, older subglacial or subaqueous delta systems and use those geometries, like using these relationships to try to say something about past discharge and like past ice sheet behavior?
Yeah, so that would, I would point you to the Normando 2019 paper. So they did do some imaging on some no longer active fjord delta systems. And a lot of the deposits on the delta front are reworked by the time that they're imaging. And so we can see kind of faint signatures of what the subaqueous transport network was. But we would, there might be some techniques to extract that information so long as they're not too reworked. But it's a really good idea.
I was wondering if there was any sign of winter discharge at all. I know you were there only in the summertime, but there's this kind of new idea that the ice sheet is producing a lot of melt in the wintertime now. And I'm wondering if that's potentially mobilizing sediment in the winter, if it's all the activities happening in summer, if you know.
I do not know, but I will speculate. So I've wondered, in systems where we can establish really persistent channel networks, if there's any role of either winter or early season flow underneath ice cover that's playing a role in maintaining those kind of persistent channel networks.
Any other questions?
I thank you for the talk. I don't know much about glaciology, but I was wondering, you have these two like end members. Is it a hard switch between your end members, or are there a range of different diffuse versus persistent streams you would see? What would an in-between member look like?
That is a great question. And to be frank, I need more bathymetry data. So that's something that I'd like to embark on with Alexander Normando, just in terms of it basically playing the same game with hopefully something that is in between. It's not clear if we'll have the persistent versus kind of diffuse networks that always emerge.
Anyone else? I thought I saw somebody in there. No.
And so I'm wondering how far these sediments can be transported into the ocean and how much organic carbon it will carry.
So through the turbidity current channel network, I am hoping for some funding to actually allow me to follow that channel farther along the fjord and see if we can resolve like where a fan is building so that we can understand how far sand is transported into the system. Yeah.
Brandee, this is very interesting, and it's been a long time since I took sedimentology, but it used to be called a Balmer sequence for looking at the turbidity of the deposits. Do you think the deposits in this system would be very similar to those of the quote classic turbidity deposits, the Balmer sequences?
Yes, and so something I didn't share today is that we recently, so over the summer, we actually collected cores through the turbidity channel bed and also on the flanks, and we do see some alternation similar to what we might find in a Balmer sequence. So.
All right, well, let's thank Brandee once again. And she has a lunch coming up. If anyone wants to join, you can talk to Emily. Thank you.